Okay, I'm back, and now we want to do part 6 of the lab, which is on distance versus time graphs. Graphing is very, very useful to a scientist. So, a scientist will, when he's trying to investigate some kind of phenomenon, is going to collect data. And then they will graph that data, and then they will look for trends in the data. Now, ultimately, they would like to turn the graph into a straight line, because if you have a straight line, you can predict what the equation is. So let me show you what I mean here. That let's pretend that somehow a scientist has gotten some data and knows the numbers that goes down here and knows the numbers that goes up here. And then they somehow manage to turn it into a straight line. Well, there is an equation for a straight line. So the equation is y equals mx plus b. Y is the up and down part. X is the sideways part. M is the slope of the graph. And then b is the slope intercept. So b is going to be the distance either above or below the graph where this thing goes through it. But you see it goes through 0, 0 right there. So for this particular graph, the b would be a 0. So it wouldn't even be part of it. So there'd just be y equals mx. And then if the scientist can figure out what the slope is, then they've got an equation that relates this variable to this variable over here. So what do we mean by slope? So slope is given by the letter m, which is very bad because in physics we use the letter m to stand for mass. Well, we can't really do much about this. So I will use the geometric definition of m, which is slope. And slope is going to be rise over run. So to calculate the slope of a line, we pick out 2 points on the line. So this is going to be point number 1, and then this is going to be point number 2. And so point number 1 is going to have a value along the x-axis of x sub 1. And then this point here is going to have a value going sideways of x2. And then we could go this way over to here, and then this would be y1, and then we could go this way over here, and then this is going to be y2. And then the change in the up and down part is rise. So when you get out of a chair, you rise. You're going up. So this distance going up is going to be the rise. And then when you run sideways. So this distance going this way is going to be the run. So notice our formula is going to be m for the slope is going to be equal to y2 minus y1, and then divided by x2 minus x1. Be very, very careful. So do you see that in this first column are the 2's, and then in the second column are the 1's. So it's final minus initial. Your final position minus the initial position is the distance that you travel. And so this is going to be our formula for slope. It's going to be really important so that scientists, when they graph their data, they try to make it look like a straight line so then they can figure out what's the formula that relates the data. Alright, so now we're ready to actually do something with this. So our first thing that we're going to do is distance versus time. So going up and down is going to be called the dependent variable. And then going sideways is going to be called the independent variable. So that going sideways, instead of the letter X, it's going to be T for time, the time that elapses. And then our first graph that we're going to make is a distance versus time graph. So distance, R, is going to be the up and down part. And we want to be able to calculate the slope of a distance versus time graph. Okay, so let's go down to here. On the simulation, click on charts. So now we're going to go over to here, and let me go back to, this is what you had been seeing, this one right here. Okay, but I'm going to click on charts. And when you first open it up, it's not going to look like that. So let me, yes. All right, so when you first open it up, this is what you're going to see. And you've got three different kinds of graphs: a position versus time graph, or a distance versus time graph, a velocity versus time graph, and then an acceleration versus time graph. But this is too confusing. So we're going to start with just doing the distance versus time graph. So it says, so let's go back here. It says to type in a velocity of 3 meters per second. And the acceleration is going to be 0. So we're going to start with 0 acceleration, but a velocity of 3 meters per second. So if we go back to here, the position is 0, the velocity, so let's type in 3 for the velocity, and then the acceleration is 0. All right, so now we've got our initial parameters, and now I'm going to click off this graph. So you see here, click on there, and that gets rid of that graph. And then click on here to get rid of that graph. And if you want the graphs back, then you click on these two things. And so now we're going to run the simulation and see what it looks like. Okay, now I'm going to stop it. So you see here was the stopwatch that was showing you the time. And then down here, it has the time. So here's the time that has elapsed along the bottom, and then the distance is going up and down on there. And you notice that once it hit the wall, then it's kept on going. So it went sideways right here. So you notice the position no longer changes because he's up against the wall. He can't go any further. But the time continues to change because the stopwatch was still running. We don't care about this part, so don't worry about that part right there. Now, we want to calculate this slope right here. So we're going to go back to the lab, and it says to calculate the slope of the velocity versus time graph and enter your answers below. Now you remember, you get to pick your values. So your 0.1 and your 0.2, you get to choose any 2 points that you want to use. Well, what do you think would be a good point to use? So if we go back to here, and there's our graph, what would be a good point to use? Well, I would use 0, 0 down here, because you know exactly what this number is, 0, 0. So that would be a good number for your position R and then for your time T. Now you choose any other point along this line to be number 2. And I'll let you go ahead and pick that. So that you're going to have R2, R1, T2, T1, calculate the slope using this formula. But the difference is going to be that instead of Y2, so this is up and down, it would be R2. And then this one would be R1. And then down here, instead of X is T. So this is going to be T2 minus T1. So you're going to calculate the slope, and then just write down what was the velocity that you used. So the velocity was 3 up there. Note that the graph was a straight line. Anytime that you get a straight line, it means that something is not changing. Now the goal is to figure out, well, what is it that is not changing? So to figure out what the slope of the line represents, we're going to plug in the units. Notice that the top part of the formula involves distance, and distance is given by meters. Now that's not M for slope, it's horrible. So this is a distance in meters, and then the unit for time is the second. So we've got the units for the slope are meters per second. Now that should be ringing a bell in your head. So what is meters per second? Okay, and then so the units of meters per second is the metric unit of what in physics. So the slope of a distance versus time graph is the what of the object. So fill in those blanks. Notice the slope was positive. It was a positive slope. What do you think that means? So if you look at your thing that you just calculated for your slope, I'm not going to give the answer away, but your slope meant something, and it was a positive number. So what did it mean that the object was doing? Okay. Now we're going to click on Reset All to reset the simulation. So we're going to go back to the simulation here, and then it says Reset All here, and then click there. So now it sets everything back to 0, and we've got our 3 graphs again. All right, now we're going to go, and we want a velocity of 3 meters per second, so that didn't change, but a acceleration of 2 meters per second squared. So this time it's got an initial velocity and it has an acceleration. So you're going to have to go to the simulation, and you're going to have to enter your, what was it, 3? So 3 goes here, and then 2 goes down here, and then we're going to get rid of the position versus, or the velocity versus time graph. So let's put that away. Then get rid of this one. So we're back to our original position versus time graph, but the difference is it's accelerating. The object will be accelerating. So let's look at what happens when we do that. So let's go ahead and hit the play button. All right, now this one is a little bit harder to see. So this thing right here, that is not a straight line. That's a curve. So it's curving this time. And so that is going to be characteristic of a position versus time graph whenever something is accelerating. So if we go back to here, is the graph straight or is the graph curved? Well, if you've been listening, I just gave you that. That means that the velocity was or was not constant, and then y is the velocity doing this. Okay, so that should be pretty easy. Well, it's easy for me, so I've been doing this for quite some time. Part 7, velocity versus time graphs. So we'll do this in just a moment.